Anyway, so what we're going to do is start talking about virtual memory. And part of the reason why is because there is a lot of background. We're going to have two lectures talking about general virtual memory considerations. And I think then next Wednesday is the lecture that I'm going to devote to how to implement Project 5. Project 5 is one of the two hardest assignments. If you thought they were already really hard, they get worse. But yeah, Project 5 virtual memory is pretty challenging, and so I want to try to steer you in the right direction before before you dive into it. Because Virtual Memory Lab is the one where it says go to this directory and implement virtual memory, and the directory is empty. So it's like, oh man, and then I have to come up with everything from scratch. And it becomes straightforward once you actually consider all the components of any virtual memory system. You all know enough to figure it out, but it's daunting to dive into something like that from scratch. So that's why I think it'd probably be good to talk about that. Anyway, we all know that programs like to use memory. I mean, any interesting program is going to be using memory and not just register locations to do computations. And of course, we have variables stored at specific locations. What's interesting about that is we don't write programs against specific addresses unless you're doing the PC boot or lab or something like that. Then you might have some. Basically, we usually use symbols to represent this stuff because we don't want to have to know all the numbers. I mean, this actually used to be this way a lot back in the olden days, but it's difficult and it's definitely error prone over time. So basically, over time, you take your program and you compile it, and some things get addresses, and then you run it, and more things get addresses. Basically, the computer requires real addresses. It can't just use symbols. So along the way, addresses get assigned to things. And so the important detail here is that the OS is the thing primarily responsible for deciding how should things be laid out in memory. And it has a name. I think I must have it on the next lecture slide. But it's called the ABI, Application Binary Interface. This is specified by the OS, and programs have to be laid out in memory according to that interface if they're going to work properly. Okay, oh yeah, hey, it's on this slide. I just forgot. Okay. So, very common acronym that you'll see when you work with compilers, because compilers are responsible for adhering to the ABI and so forth. So, this happens very rarely now that you actually can have the compiler generate absolute code. And that's where the function addresses are known, the start of the binary is known, start of, all the various variables are known as well. Okay? What is much more common is that you'll have code that is relocatable. Okay? And what that means is that there's a certain step at runtime, just before the program starts running, where the operating system runtime will try to figure out what addresses things should live at, and that gets taken care of right before execution. Okay. Now, let's see how I see this. Final binding of symbols, addresses occurs. So this is the interesting step, is that, for example, you have a variable. We don't know where it lives. And the OS, or the program loader, will load that binary into memory, and then it'll actually have a table somewhere that says this is where that variable is referenced all over in the program. And so once the address of the variable is decided, then it can go through and actually patch the code. So this is a common step that occurs in many different programs. Anybody who has a Mac, this is happening like every single time, because everything is dynamic libraries in Mac. Okay. So anyway, the program includes details about what symbols are used and where they're referenced from. And it tends to be a really straightforward mechanism. It's very mechanical. I mean, this is what computers excel at. The final option, which is a really interesting one, is position-independent code. So this basically allows a binary to determine what location is it loaded at, and there's a really straightforward mechanism for doing that, and then all accesses are actually computed relative to that location. And this actually has become very common. Relocatable code was much more common in 32-bit, but what happened is when we moved to 64-bit, relocatable code required too many large constants and large values to be encoded. And so a lot of programs now are using position-independent code. 64-bit x86 processors have this whole thing called RIP relative addressing. So as long as you know the distance between the instruction and the thing that it's accessing, there's efficient ways of encoding that in the binary. And so that's become even more common now. If you need to figure out, so RIP relative solves certain problems, but the simple way that you can find out what your address is just call the next instruction and then pop that address off the stack. It's a very common trick. That goes way back. I remember a lot of computer viruses that would do that kind of thing. Okay, so ELF is the format that we talk about, and that'll actually also become really important because ELF sections correspond to the various segments of your program. Data, read-only data, .ro data, .text, your program instructions, and so forth. Okay, so on 32-bit Linux, you have executable object files. Again, the ABI of the operating system says it has to start at a specific address. Okay. That's what it is on 32-bit Linux. On 64-bit Linux, it's like 400,000 or something like that. So it got moved down a little bit. Relocatable object files. So these tend to be your .o files that generated during compilation. And those things will basically, like .data will always start at 0. .text always starts at 0. So the code segments actually overlap. They're intentionally designed to allow relocation during a linking phase. Okay, so relocatable object, you can't load. That's why you can't run a .o file. It's just not finished. Okay, and then shared libraries tend to be with position-independent code. And then Windows has this, you'll notice that there's a lot of, I don't know, the file formats, the binary file formats tend to have interesting names. So you have ELF, there's another one called Dwarf, there's another one called COFF, C-O-F-F, and Windows is less creative, although I think it might be based on one of these earlier formats. Portable Executable. And that basically, again, allows you to do both absolute and relocatable programs. With the interesting detail that Windows programs prefer to start at a specific address, and so that's what the OS will load them at if it's possible to, if there's not an overlap with a shared library or between shared libraries. But they also support the ability to be rebased. I think I might say that on this, yeah. So rebasing just involves going through and updating all the addresses that instructions refer to change the base address that the binary uses. Now, one thing that I want to point out here as an aside is you'll notice that OSs and binaries need a lot of management. And that's one of the things that you'll notice. You probably take this for granted unless you've had to dig into this already yourself. But there's a lot of modifying and updating binary files, sequences of instructions to support all the machinery that's necessary to load a program and run it. Okay? That's one thing that you should be happy. You have very little of that to do in Pintos. So everything's statically linked. You have all of your library code is linked into your program so that you don't have shared libraries. You don't have things like that to worry about. But real OSs, in order to try to reduce duplication of code and to increase maintainability and so forth, they have a lot of this stuff that they have to deal with just to try to make the system a little bit more manageable and maintainable. So it's an interesting thing. I wish we had time to give you some lectures about it because there's some really interesting features that you run into. Okay, like the way that shared libraries are hooked into binaries is really interesting. One shared library that's shared with like a bunch of programs all running at the same time. Okay, so programs. We have a program running on a CPU, and as we all know, these use logical addresses or virtual addresses. Either term is correct. But basically, the program is incapable of using absolute addresses because the CPU is presenting an abstraction. It's not possible for the program to actually emit an absolute address. That would require the OS to configure the processor in a particular way, so that's possible. Okay? So the computer memory receives physical addresses. That's what the CPU emits. And there is this thing that we affectionately call the memory management unit that actually does this address translation. Okay? So the MMU, I'm just drawing it as a box right now because it actually can work in a lot of different ways. It's something that, if you remember CS24 or any of our earlier discussion, we're familiar with one way that it does translation. and that's through paging. But it turns out that there's been a lot of other ways that this translation has been done through the years. And it's kind of a neat mechanism, a neat little subsystem built into the processor. Before we talk about it, though, I want to ask the question, like, why would we want virtual memory in the first place? It turns out that there's more than one reason why we would like to have virtual memory. And we've talked about a couple of them. Anybody remember some of them? There's a few really obvious ones, and then there's actually another one that I'll point out to you as well. Like, do we want processes to be able to work with each other's memory directly? No, right? So that's an obvious reason for having virtual memory. Address space isolation. What about the whole notion of a process's working set? Do processes actually use all the memory that they actually may have allocated to them at any given time? Again, the answer is no. So another thing we can do is we can swap out parts of processes. We can demand assign frames to processes based on their needs. So again, you get this benefit that we can overcommit physical memory, and generally it'll be okay. So process address space isolation, that's one obvious reason. Okay? We should be able to protect processes unless they explicitly agree to coordinate with other processes. And by running them in separate address spaces, it becomes impossible to actually share information between processes unless they actually want to. Okay? And that's really important. In fact, I think that one of the extra credit options, I can't remember if it's extra credit, I think it is, for Project 5 is building shared memory in the virtual memory system. Thankfully, with our hardware, it's not impossible. It's actually quite feasible to do. Okay, so yeah, each process virtual address space mapped to a separate region of the physical. So again, we have the physical address space, and then each process has a view of that. And then by controlling the mapping, we can assign each process to a different region. They can't overlap unless the kernel explicitly configures it. So, and this is all protected operations. You can't write, so I think it's control register 3 controls the memory mapping on x86. You cannot write that register without having kernel level access. Okay, so that was the first one, process address space isolation. Second one, since they do run in different address spaces and they can have whatever view of memory we want to give them, that makes it really easy to implement the application binary interface. We can do things like say every process starts at this address. We can say the stack always starts at this address because every process can be given that view easily. The view of memory is different. Or I should say it's an easy abstraction to implement on the hardware. So yeah, all the binary programs can be laid out with the same structure and pattern. This is something that you'll notice, and you probably already saw this in system calls, right? C0000000 is a number you should recognize because that's what is a fizz base. Above that is kernel, below that is user space. Okay? And so it makes sense that the stack would start at the highest address and grow downward. And you might say, well, but C0000000 is in kernel space, and that would be accurate. But remember that when you push something on the stack pointer is decremented first, and then we store the value. So it's always going to be on the user space side of that fence, if you will. Okay, so this is a nice thing. We can have this nice, simple ABI. If we had to care about how everything fit in memory, we wouldn't be able to do this. So this is a huge win. This makes it easier to write compilers and linkers and things like that. Okay, third benefit, and this is the one that we talked about a little bit as well. If I have a virtual memory addressing mechanism, then I can move stuff from main memory or physical memory to secondary memory or the disk. There's a lot of different terms for these things. And we call that swapping. So we can actually move stuff out of physical memory and free up that space for something else. Okay. So these are obvious statements. Program must be in main memory to run. Where are the instructions loaded from by the processor? Well, it has to be in main memory. But if the process isn't ready to run or it's not using some part of its address space, why not save that on disk? And in this case, we call it a backing store. And we can save some of the process's context on that backing store, and then that frees up physical memory for other processes So this is a big benefit. It allows us to overcommit memory, and in most of the time, I mean, it's just like a bank. If everybody went to the bank and asked for their money, we'd have a huge problem because the banks overcommit the available money. That's fine because most of the time people don't want to do that. The same thing with processes accessing memory. Since processes usually don't access their entire address space, it's perfectly fine for the OS to overcommit memory. Okay, so scheduler switches to a new process. Well, the dispatcher can say, is this process actually in memory? Or at the very minimum, is the stack, the part of the stack being referenced, is the part of the program being referenced, are those things in memory? And it can go ahead and start paging those in. Okay? So we'll talk about some of these details in the future because there's a lot of variety. There's a lot of flexibility in how to implement it, and so there's a lot of variety in how OSs do implement it. Okay, so yes, this is the whole idea. I can overcommit memory. Memory used by all the processes can exceed the total physical memory in the system. And so that basically is a great idea, especially since we want to achieve a good process mix. I don't know if you guys remember that term, but a process mix is simply having a good combination of I/O blocked processes or I/O intensive processes and CPU intensive processes. Getting the right mix basically allows us to execute the CPU intensive tasks until I/O unblocks, and then we can execute those, and then we go back to CPU intensive tasks. So it's nice to be able to achieve a good mix. Okay, the only problem though is that the peripherals used for storage, swapping, are slow. And that should make total sense. It's like, well, why don't we make those faster? Well, if we made them faster, we'd just use that for main memory and make the main memory bigger. But even something like a solid-state drive is going to be, if I remember correctly, like 100 to 10,000 times slower than your main memory. So that would be nice to use for a swap, but it's still going to be much slower than talking to main memory directly. Friday, my brain is burned out. Okay, so swapping takes time. So there are a couple of different strategies for swapping. And one that you probably have never heard of before is called standard swapping. And standard swapping actually involves moving an entire program. So you have all the addresses, all the information, all the data for a particular process moved out of the physical memory onto the swap device. Okay? That's standard swapping. Nobody does standard swapping anymore because it's just too slow. It could take even on the order of seconds. If you were moving like a multi-gig address space to disk, even with a fast device, that's going to cause a significant pause. Okay, so generally we don't use standard swapping anymore. The other problem with standard swapping is the whole notion of a working set. We recognize that a program will only be using part of its available address space, and it may be using some of it really heavily, and the rest of it doesn't care about. So standard swapping doesn't allow us to get the granularity of resource utilization that would actually allow us to efficiently manage these resources. So standard swapping was the wave of the future back in like the 60s and the 70s when this stuff was all relatively new. But we don't do it anymore because it's just not granular enough for us to manage resources efficiently. Now, another little side detail, lots of people have smartphones. I see smartphones more than I see computers in classes. And even though you have this obviously doesn't have a spinning disk in it, right? That would be dumb. It still has virtual memory. And it still uses virtual memory for all the reasons that we've talked about. I mean, it's nice to have an ABI, even for mobile devices. They're quite sophisticated now. So being able to compile all of your apps into a single unified format so that they're easy to load and easy to compile makes a lot of sense. And you also would like to have address space isolation. I definitely don't want my bank app to be accessible by my random social networking app that maybe I trust and maybe I don't. I mean, that would be a really bad idea. So typically you don't see swapping on mobile devices. You see maybe a limited version of that on Android devices. iOS tends to be a lot stricter about this stuff. The main reason why is because they may have a flash memory to use, kind of like a solid-state drive, but they're not really, it's not very large, and they want to make sure to utilize it for persistent data as much as possible, you know, your databases and so forth. So they tend not to do swapping as much. Like I was saying, OSs tend to be a little bit strict about this stuff. So mobile OS, when it needs more available page frames, for example, because a process is using more memory, then it will go through and ask processes to relinquish memory. Like, can you please clean up after yourself? Give me back some memory. And sometimes if a process is like, no, then the OS will say, okay, well, nice knowing you, and it'll just kill it. And I don't know if any of you have noticed when you're using your iPhone or your mobile device, maybe an iPad or something like that, that sometimes you'll be using an app and it'll just go away. It just goes away. So sometimes what that is the app crashing. That does happen because apps have bugs just like any software. Sometimes it is the OS just saying, I need memory, dude. It's just like, you're done. So that sometimes happens. I remember that used to happen a lot on my iOS devices running Safari, but now I use Chrome. I don't run into that nearly as much. I don't know why. Okay, so yeah, Android may use some limited swapping, like I was saying, if it wants to be able to restart a process quickly. So sometimes you'll see that. Okay, so yeah, you can imagine that mobile devices place more stringent requirements on application memory usage. You don't want to have an annoying interaction with the user. Okay, so that's a general coverage. Does anybody have any questions about any of that stuff at this point? All right, so let's talk about strategies for memory management. Because it turns out, like I said, there's been a variety of strategies used through time. And I always like to see the historical perspective on these things, because a lot of times when you start learning something, you don't remember the old ways that people have tried things, and you think you've invented something new, but it's been around since, you know, the 50s or something. So very simple strategy is, I have physical memory and I have virtual memory. Why don't I just take the virtual addresses and shift them by some constant? Okay? So that's called relocation. And so you have one register. So your entire virtual address space is all shifted by one value using the relocation register. And so your physical address is just your virtual address plus this relocation value. That's all we do. Okay. Now you could also introduce a second register that holds an upper bound on the virtual address space so that you can then have sort of where it starts and where it needs to end. So like I have here, a virtual address, if it's above the limit, raise a fault. Otherwise, just compute the physical address from the virtual address and the relocation value. Okay. And obviously, the relocation and limit registers would be protected so that only the kernel is allowed to do this. Okay. So this strategy, this simple relocation strategy, is actually all you really need to be able to run multiple jobs at the same time on a processor with protection levels and memory management unit. Okay. So this is a very basic approach, and you'll notice that this is simple enough. This is like the initial way that things were done. I mean, it was enough for people to start introducing a certain basic level of multiprocessing. Okay. So programs compile with absolute address, blah, blah, blah. When the program is executed, the OS chooses the value for the relocation register, takes the limit value from the program that's being loaded, off you go. Now, some interesting questions immediately emerge from this. When your program needs more memory, like you call malloc, I want to allocate 100 megabytes. Well, it may be that the initial program virtual address space didn't include those addresses. And so now the OS has to extend the size of that. How does that work with this? You see how it can be more challenging now to increase the size, the available memory that a process has. So relocation is pretty limited. Like, it does the minimal necessary, but it has some severe limitations when it comes to the way that programs generally work. Okay, so like I say here, the processes are isolated, and so that's cool. This is called contiguous memory allocation. Processes, like it says, occupy a single contiguous region, and they can be put adjacent to each other in the physical address space, but one process's memory is going to be contiguous, and they're not interleaved like we have with our modern approaches. Okay. So one issue that you have with this is actually similar to allocator issues. Remember, I allocate memory regions, varying sizes, they have different lifespans, so allocate, release. Over time, you get a whole bunch of little fragments that are difficult to utilize because you can't smush together the regions of memory in use because people are using them. Okay? So fragmentation can become a big problem with this allocation mechanism. And like I say on the slide, you can do first fit, best fit, those kinds of things. There turns out to be another strategy that's actually really interesting. Because remember, when you're talking about an explicit allocator, the problem is somebody may have a pointer into the middle of a memory region or have the address of the memory region in some place you can't identify. So you can't really move the memory regions around. But it turns out you can move these memory regions around. Just need to change the base, like the relocation register, and you can move things around a little bit. So we'll talk about that in a second. This also requires, notice there's no option really, it requires standard swapping because you can't really say, I want to just swap out this part of the process. Okay? So that's pretty annoying as well. Standard swapping kind of goes hand in hand with this contiguous allocation mechanism. Also, what about shared memory regions? Well, maybe I could have the end of one process overlap with the beginning of another process. That'd be terrible. But one could try to do that if one needed to. So you can see that this has some pretty severe limitations. Okay. So, but this was still, like I said, perfectly sufficient for initial computers that had multiprocessing so that they could implement address space isolation. Okay, so that's one. Now, all you need to do is take this idea and tweak it slightly, and suddenly you get a whole bunch more power. And so the more advanced version of this is called segmentation. Basically, addresses all have a segment number as well as an address. Okay? And you may recognize this from x86. Like x86 has a segmented memory model. It's really good at this kind of thing. So addresses have a segment and an offset. And the segment is used to select a specific base and limit pair used to describe that memory segment. Okay? So now you have programs that can have multiple segments, and each segment has its own virtual to physical mapping. Okay? So you have a segment table that is used to look up the corresponding entry. You pull out the limit. Is the virtual address below the limit? If so, we're good. Pull out the base and add that to the virtual offset, in this case the offset, and you get a physical address instead. And so processes have their own segment tables, and again this is protected by the kernel. So only the kernel can set up the segment table for a process, only the kernel can manipulate it, only the kernel can switch between segment tables when we do a context switch. Okay, so this already is starting to make things a little bit more powerful. Okay, there can be various characteristics you specify for segments. Basically, all of this recognizes that programs have different kinds of data that are used in different ways. Okay, you have the program text, code. You have constants read-only data. You have global variables, which, like you say, are read-write, not executable, and they tend to be assigned absolute addresses. Memory heap, which is dynamic, grows and shrinks, tends to be read-write. Probably shouldn't be executable, but you know, programs. Then you have your program stack, which definitely shouldn't be executable and tends to be manipulated in specific ways. Okay? So we have these different segments, and so you think about x86, you have CS, DS, ES, SS. So already we have code segment, stack segment, data segment for all of this kind of junk, and you have various other ES, FS, and GS can be extra segments used for other things. Okay? So you can have these segments that are used by a segmented memory model to, again, do process address space isolation. Okay? So this is nice. This is already going to be much better than the old model. Okay? First interesting observation, no longer do the memory regions have to be physically contiguous. You could have one process's code segment and then another process's code segment, and then a third process is stacked. That's all perfectly fine. Okay? So this does help mitigate fragmentation, because if I have smaller chunks, then it's more likely I'm going to be able to find an area of physical memory that's available to take advantage of. Okay. Shared memory becomes much easier too. Because like I said, if you have segments that are devoted to specific things like code, data, stack, and then you have extra segments, then you can use those for doing shared memory between processes. Okay? So that becomes really useful. And you can start doing more inter-process interactions more easily. Now swapping, not terrible. Now you can start swapping individual segments, but there are going to be segments that are large, like the memory heap is going to be large. So your data segment, you still have to swap the entire thing, and so that's going to take up some space. Okay? That means it'll be a little bit slower to read and write. Okay? Any questions about this approach? So again, thankfully, we don't do this. This is not the way that we generally do things. It turns out that you can actually deal with fragmentation issues in virtual memory systems pretty easily by just moving stuff around. This, again, was the thing you couldn't do in a heap allocator in a single process, because you can't really manipulate the address space. But since the kernel can manipulate the address space, it becomes easier to move things around. Okay? So we have this mechanism called compaction. What you can do, like, let's say you have a process and you end up having a little bit of space before it. You want to coalesce free space upward or something like that. Well, when that process isn't running, the kernel can go ahead and just copy everything down and adjust the start of that program segment or segments. Okay? Then it becomes really easy to move things around. You could even do something really slow where you swap stuff out and then swap it back in if you wanted to sort of compact things properly. But generally you don't need to. You can just copy things around in memory, and that should be perfectly fine. Okay? So this is nice, because if I have the available memory more compacted together, then I can allocate it to other processes more easily, so that should increase the number of processes I can run. Okay? So not terrible, not great, but an option. Okay, so that's really nice. Okay, so this is what we wish we could do in an explicit allocator. We can't. We can do it in garbage collecting allocators if they're not, languages like C and C++. But the OS has a lot more capability because it gets to manipulate this virtual abstraction. Okay, paging. This is the one that everybody tends to use for obvious reasons. Plays well with external storage, swap devices. It plays well with these external fragmentation issues just vanish because all the pages are the same size. Okay. So we get a lot of benefit out of this paging approach. Okay. Now, some important terminology, and we're going to be using this over and over again, so that'll help you guys cement it in your heads. But when you actually have physical memory regions, like blocks of physical memory, we call them frames. And the way that I like to describe it is, it's like having a picture frame, and you can put whatever picture you want into it, but the frame is where you put pictures. And it's the same thing in, this is probably actually where these terms came from, the people who originally designed these things. I want to store some memory for a process, put it in a page frame. That's where that goes. And the actual data is called a page. Okay? So blocks of virtual memory are called pages. Physical memory blocks are frames. Sometimes we call them page frames. Sometimes for the sake of simplicity, we just call them pages as well, but like physical versus virtual pages. But the correct terminology is really to call them frames. And somehow, by magic, we take a virtual address, and since the frames and pages tend to be a power of 2 in size, we have some number of bits that are the offset that just translate directly over. We don't need to do anything with them. And then we have some mapping of virtual page number to physical page number. So again, the question is, how would we formulate this mapping mechanism? It turns out that there are a wide range of mapping options that have been explored. The ones that we use nowadays, people seem to have settled on. And they'll work for quite a while. I'll point out some of the issues that we've started to run into with them. So like I was saying, paging makes it really easy to never worry about fragmentation. Okay? I don't need to worry about little tiny fragments accumulating over time because everything is always the same size. Okay? Memory is always allocated, released in page-sized chunks. You may have some internal fragmentation. And this is kind of an interesting thing. Different programs do this differently. That you'll see things like .text always rounded up to 4096. Or you'll see .bss, well, BSS doesn't, oh yeah, even BSS counts. It still needs an address range. .data, .ro data will be rounded up to a multiple of 4096, so that it'll be a whole number of pages. Okay, so you do run into that. So that does generate some internal fragmentation, because if my program needs 64 bytes of global variables, then I have to give it a whole 4 kilobytes. I can't avoid that. Okay? Thankfully, that's not a huge deal in practice. 64-bit operating systems seem to be able to do this a little bit more sophisticatedly, but this is the one issue, is that you do get a little bit of internal fragmentation. So what people tend to do is pick a page size that's small-ish, large enough to make swapping efficient, but small enough that we won't run into real serious internal fragmentation issues. And it's interesting because depending on the need for the page and the address range, some processors actually support different page sizes. Like if I remember correctly, on 32-bit, you can do 4 kilobyte or 2 megabyte pages. So if you have an area and you know you need large buffers, you can just use 2 megabyte pages. Same thing with 64-bit. You can actually have multiple page sizes. The smallest is 4K, but then there's various other page sizes available in the system. Annoying. Okay, so if you have a system that's really simple, then the way of mapping virtual pages to physical pages becomes really simple as well. And I think this is kind of funny, but like really old computers, the PDP-11 is a great example of this. Address space, 64 kilobytes. That's all it could access. Pages were 8 kilobytes. Well, if you only have 8 kilobyte pages and only a 64 kilobyte address space, you really only need to have 8 registers, and then you can specify the entire mapping. So that becomes really easy, and the processor can hard code how it uses those registers to just build in the memory mapping mechanism. So PDP-11 was kind of an interesting processor from that perspective, that you just say, here's the mapping and registers, and it just enforces it. Okay. But most of the time, we have physical memory that varies in size. We have a specific address range. But physically, we may have 1 gig, 4 gigs, 16 gigs, whatever, and it could vary. And so it tends to be that people specify their mappings in page tables now. Okay. So we're going to spend a lot of time talking about page tables for the rest of this lecture. The one major issue with having a page table is that it's stored in memory. Remember, memory access is slow, and if we involve memory accesses to do address translation, that's going to make memory access even slower. And so a lot of times these systems introduce translation look-aside buffers. And that way, when I see a virtual page number come in that I recognize, I can just pull the mapping out of the translation look-aside buffer as opposed to going and looking it up in the page table. Okay? So TLBs are actually really crucial for doing this address translation efficiently. Okay, so talked about that. If it's not in there, you get a TLB miss. This is another thing you might find interesting. Some processors are able to resolve TLB misses themselves. So x86 processors, no problem. They can handle that themselves because the page table mapping is specified in the spec, and you just follow the layout. So the processor can do that easily. There are other processors that have more complex page table mappings, and so they can fire an interrupt to say, hey, kernel, I ran into a TLB miss. Can you help me figure out the virtual to physical mapping? So if you think about it, you actually have an interrupt handler running when a memory access fails. So this tends to be older systems that had interesting and different ways of specifying the memory mapping. Okay, this is the simplest kind of page table. So single level. Virtual page number is just used to index into that page table. Okay? Whatever the value is there, that's the physical page number that goes into the physical address. Okay? This is about the simplest you can possibly get. The problem is, as your address space grows, virtual page numbers grow, the number of entries you have to have in your page tables grow, the size of the page table entries grows because now I have larger physical page numbers, and so this whole mechanism becomes expensive really fast. Okay? So this is a dense representation. This is just a little bit of math to show you that on 32-bit, you would end up with page tables taking 4 megabytes apiece. 64-bit in Linux, they would end up taking, what is it? I think it's 512 gigs, I think is the size. 512 gigs, that's like half a terabyte just for a dense, simple page table. So because of this, most processors that have larger address spaces incorporate hierarchical paging. Hierarchical paging just means that we turn this dense data structure into a sparse one. We take the virtual page number, break it into regions of bits, and use each chunk of it to index at a particular level in the page table hierarchy. Okay? So that's the idea. Now, this being a sparse data structure, the number of nodes in this structure is actually usually pretty small for most programs. So you save a ton of space. Okay? So I talked about all of this. Yeah, memory area is unused. The corresponding page table entries are empty. Okay? Any questions about this? This is going to be important for you in Project 5. This is what the IA32 address translation mechanism looks like. You have page directories, and then you have page tables. Okay? So page directories take, what is it? I think it's 12 bits of the address to do the entry. Page tables then have 12 bits for those entries, and you have this tree structure that's used for specifying the virtual to physical mapping as opposed to just a single table. Okay. Oh, I'm sorry, I got the numbers wrong. So 12 bits is the offset, and then you have 20 bits. So yeah, so it's 10 bits per level, and then you have 12 bits for the offset. Make sure I get those numbers correct. Okay, so that's 2 levels, page directory and page table. x86-64 has a larger address space. Notice it's 48 bits, so I think that's 128 terabytes it can access of main memory. And since it also has 4 kilobyte pages, it has a 4-level page table structure. Okay. Now the thing that you notice is the more levels I have, because I'm trying to keep my page table structure from growing out of control in its size, the more levels I have, when I have a full-on TLB miss and I have to do the full address resolution, I have 1 memory access per level. And so 64-bit, I've got 4 levels. That's 4 memory accesses that I incur in addition to the memory access I want to perform. So you can see that this starts to make it terrible. I don't remember if I have this in. No, I don't have it in the lecture slides. They're in the notes for the slides. There was a Spark processor with 64 bits of address space, so full-on 64 bits of address space, and it had a 7-level page table hierarchy. Okay. So every time you have a full-on TLB miss, you can't do a partial hit or anything. You have 7 reads that you do before you can finally do that 8th read that you really intended to. So now your memory accesses already being slow would now be 8 times slower. Terrible. Nobody likes that. So page tables, that's why I'm saying, like, this is the wave of the present, but we may not stick with this for particularly long as address spaces grow. And there's been a few things that have been explored. I'll have to give you a really quick tour of these just with how little time we have left. But some processors would use a hashing mechanism instead of a table lookup mechanism to try to map virtual pages to physical pages. Now, I imagine many of you have written hash tables. All of you are probably familiar with the various approaches for it. Can you imagine a processor navigating a hash table or modifying a hash table? The answer is generally no. And so it tends to be that, let me throw this up here because the bottom point is the one that I'm actually interested in. Usually the processor would fire a TLB miss interrupt and then have the kernel manage the page table for it. Do the lookup, do the modification. Okay? So hash page tables typically would require kernel intervention. Now that makes things slow too. So you can see it's difficult to solve this problem efficiently. Clustered page tables is a simplification, just the notion of having a bin of values for each hash. So maybe you have 16 mappings in each bin as opposed to just one mapping. So this is kind of your open addressing mechanism for hash page tables, and then a clustered page table might be your bins that you could use instead of just having one value. Okay, so this is one approach that was used. Then you have another one which is even wilder. It's called an inverted page table. And basically, if you think about it, if I've got a virtual memory mapping, then I'm going to have entries mapping from virtual pages to physical frames. What if I turn that around and have just a single array with an entry per frame, and each entry says which process is using it? So it says the virtual address of the process that's using it. So that's an inverted page table. Now the problem is, and you'll see this next Wednesday, I hope, when we talk about how you design a virtual memory system, that you kind of have to go both directions on these systems. You have to be able to look at frames, so this is good for that, but you also have to be able to go from virtual memory page to physical page to do the mapping. And inverted page tables aren't really great at that. And so, so let me just throw this up here real quickly. Frequently, you would end up having to introduce a hashing mechanism just to get into the appropriate entries of the inverted page table. Okay. So this was a really annoying issue that had to be resolved with an inverted page table. Okay. So again, you can imagine why we don't really do this. Now the last thing I'll tell you, and then I'll let you go, is that they have a second problem, which I find highly humorous. Basically, if you say each physical page, remember you have this mapping and it has physical frames, and each entry says what virtual address, what process and virtual address this maps to. Well, the problem is, since each page only maps to one process, how do you do shared memory with this? Because shared memory is all about saying multiple virtual processes map to the same physical frame. So it turns out that there are various techniques. The one that is coolest is basically on a particular processor. Remember that each processor has its own MMU. Right? So each processor is doing its own address translation. Well, that means that there's only one program running at a time. So when a program switches to be running on the processor, the kernel can go into that inverted page table and make any shared memory regions look like they're that process's memory. When it switches away from that process to another process that uses the same shared memory, then it just updates the inverted page table again to say now this process owns that memory. So you can always sort of like say just ahead of the process that's about to run and say, okay, now the shared memory is yours because you're the one with the processor. And so that was a clever technique that was invented to deal with this kind of problem. Okay. Let's see, what else do I want to say about this? Yeah, I'm glad we don't do this, but this is why I want to talk about this a little bit, is we're all used to the notion of a hierarchical page table structure. And it has a lot of benefits. It's a straightforward, especially if you have little functions to manipulate the page table mapping, which Pintos has, then it becomes easy to manage virtual to physical mappings. But the problem is address spaces are growing, and so we're going to run into some difficulties as they get larger And as you can probably tell, we don't have a great solution yet. The solutions that we have at present are kind of mediocre. So that's something important to be aware of. Okay, let me see if there's anything else. Yeah, so next time we will continue on. So I'll see you on Monday.